Okay, all right. Finally, Zoom has started. Hopefully this starts. Oh, nope, I just turned off the camera because of course I did it. Yeah. Come on, camera. Okay, supposedly we're recording and supposedly everything is working now. And ready to go. Perfect. Okay. So, synchronous communication. So UART is asynchronous. Now, this can be tricky because you may think that you are talking about different things when using the word synchronous or asynchronous. For example, you may have built your reset synchronously or asynchronously, right? Synchronous reset means that you only trigger a reset if there's a rising edge of the clock while reset is asserted. Asynchronous means that it is on the reset is in the sensitivity list, so it triggers regardless of the rising edge of the clock, right? The reset being synchronous or asynchronous does not define the communication protocol, it just defines your state machine. More specifically, the reset condition for your state machine. UART is asynchronous. This is because it can start at any time. The receiver is just sitting there waiting for the line to drop low, and it knows that it's about to start. There is no clock for it to synchronize to. So if you run a very long packet, unless your clock is exact, which is impossible, right? You're gonna have some clock drift, then eventually you're gonna fall out of range and you're gonna start getting bad data. Eventually we'll come back around and it'll start being good data again, but you'll lose it. Now, we do teach ways that you can do clock recovery. Actually, I'm trying to think, I think they teach it in digital communication now. There's a thing called phase lock loops that can be used to build a clock recovery circuit that as long as you have enough alternations between 0 and 1, it can calculate your clock speed. And even if there's drift, it can update. That is used for asynchronous protocols. What we want to do here in this upcoming lab is we're going to build a synchronous communication standard, meaning that there's going to be an extra line called clock that sends from the controller device to the peripheral device to tell it when to sample the data. Now, this interface that we'll be learning first, we're going to be learning two. The first is SPI, Serial Peripheral Interface. The second one will be I2C, I2C, however you want to say it. And they have different advantages and disadvantages. SPI has a wonderful advantage in that it's reasonably fast. In fact, it's much, much faster than UART. So UART in general, the reason that I have you guys do the baud rate of 115/200 is simply because it is the fastest that you can go without any real considerations. Theoretically, you can get UART up to like 4 megabaud roughly if you're really careful. I've never pushed it past about 1.2. Well, just 10 times what we're at right now, actually. And even that, you start getting errors. And so then you'd introduce parity in error checking, right, in the resend packets. It has problems. It is actually very difficult to start getting UART to go quickly. SPI, I've comfortably run in the 10 meg range, and you can, I think I have students in a senior project doing 400 megahertz clock range. I mean, you can get fast with SPI because as long as your clock trace and your data trace are the same length, whatever delay that happens over them is the same, and you can maintain signal integrity, right? So this is a example of SPI. Now, there's some vocabulary that I need to introduce, and I learned SPI a long time ago. So I will start with the new politically correct terminology. So see this, SCK is clock. Copy is controller out, peripheral in. So in SPI, there is a controller device and then some number of peripheral devices. So if I go click on this one, now we're getting into the not so politically correct terminology. Controller, also called master. Not entirely questionable there, but you get over to slave and you start getting some socially sensitive terminology. So we've turned from MOSI, master out, slave in, master, then MISO, master in, slave out, to copy, right, controller out, peripheral in. In order just, so you will see both. The other one that you will see is SPO/SDI, serial data out, serial data in. The reason that this one exists is for the same kind of reason, but it lacks the clarity of which perspective are you coming from, right? Because MISO and MOSI or copy, right, if you're doing those, communicate the perspective. It is the master out, slave in, okay? It allows you to then add this thing called chip select. In this case, this one's a little bit weird. So what the chip select or serial select is, you'll see CS, SS generally, is an active low signal, just like in UART, where it's going to drop low to let something know that data is coming. But it has this added benefit of you can have this only has one, but I could have CS0, CS1, CS2, and send each of those to a SPI device, a peripheral device, separately. And so one controller can alternatingly select different peripherals or slave devices, okay? So this allows you to do interface to many devices with one controller. Yeah.
Why are they daisy chained unlike like a bus for MOSI? It's
yeah. So this is, I don't actually know what device this is linking to.
Would it normally just be a whole bus of MOSI?
No. So let me go see if I can find a better example real quick. Here we go. So here we have the serial select, multiple of them. So if SS1 drops low, then the slave one or peripheral one would say, okay, it's my turn to look at the data. Now they're all getting, so this bus, the master out, slave in bus is universal, as is the MISO. They all are shared. It's just that when these devices only activate if the chip select is low. So if the chip select drops low, then it goes, okay, let's say we drop SS2. So the slave one is going to be not care. My signal is high. I don't care what's happening on the line. I'm not going to send anything out. Now, if you think back to 2700, we had these things called tri-state buffers, right? Which are buffers with an enable signal. What that does is at the output of the master in, slave out, or peripheral in, controller out, right? Sorry, I'm not good at the copy terminology because I grew up on MISO MOSI. Anyways, the master in, slave out is sending data this way. So the chip select drops low, that means this one and only this one is allowed to enable its MISO because it's going to send data back to the controller. The master is going to then send out to its peripherals, all of the peripherals, but only the one with the low chip select is going to care what is appearing on that data line. So the advantage to this one is the ability to control many devices. The downside is if I was trying to update those devices, I have to divide, like if I wanted to update them all kind of in sequence, my update rate is tied to the clock speed and the number of devices that are tied there. So like if these were digital to analog converters, which is what we're going to design for, which is a device that takes a digital input and outputs an analog voltage, right? We're going to send a digital value to one of them and it's going to update its output. If I wanted to put out 3 different signals, then I have to update one at a time. But I have to send first one, update, send the second one, update, send the third one, update. So it takes a while to update each of those. So it is a little bit slower when you have many devices, but overall it is a very fast communication protocol.
So you have a line for each chip select. You're not
Yes.
sharing chip select. So that's the downside, is you have to have as many chip selects as you do for.
Yes, exactly. Yep. Yeah. So I2C, which we'll talk about later, does not have this issue. It does not have an extra line for every device. What I2C trades off is it has only one line, which it has MISO, MOSI, and clock, and that's all. So it loses extra lines. The trade-off is, how do these other devices know that the data is for them? It sends an address. The very first part of the block is an address, and every chip will read that in. And if it's its address, it will then keep listening. If it's not its address, it will disregard. So that's the trade-off. So SPI is, fortunately for us, the easy one. You can do a SPI in like 3 states if you're really ambitious. I don't recommend doing that many. You guys are actually very lucky in this one because you are only sending data to the DAC. So the labs I built are very simple, right? Had you build a receiver, then I built a transmitter that you had to know how it worked in order to get the receiver. This one, we're building a synchronous communication that only transmits. And then we're going to be, the next one, I2C, is transmit and receive in a serial communication. So I'm slowly building you guys up, so there's no big cascading surprise of difficulty.
Unless you're super behind.
Unless you're super behind, which I hopefully we're avoiding this time. So there are several different versions of the protocol for SPI. In fact, there are 4. This one is back to COPI and SIPO, which I'm never going to remember, but I will try for the sake of the modern generations. So here we have clock, right? It's just going to have a rising edge for each and every bit that it wants to transmit. It's going to have, this is really terrible. Why doesn't it have the chip select? I don't want the chip select. There we go. So if you don't know, you can do this thing most of the time where you can open image in new tab in Google, which then only opens the image, so you don't have to browse the whole web page to figure out where that is. Okay, so these are 2 different versions of SPI, 2 different modes, but we'll focus on one. So the clock is on the top. As we know, we can trigger either on the rising or the falling. We don't like to trigger on both, right? That causes some issues, and many of you had that issues in your last state machine. So the red line then is the rising of the top and falling of the other. What this means is the SCK can change its C-pol, which is clock polarity. Which clock polarity do I care about? And then we need to determine where we're looking to sample. So let's look at this one. In the CPHA is 0 and C-pol is 0. That is the mode 0, 0 for SPI. There are 4 modes, 0, 0, 0, 1, 1, 0, 1, 1. Okay, and those are tied to, let's look at 0, 0 because I'm pretty sure that's the one we have to build for our data sheet, or sorry, for our controller that we're doing in the lab. So if you look here and you have a rising edge of this clock, because we're on 0, you will take data bit 1. Okay, you will read whatever's here. This kind of bracket looking shape is a bit, part of the payload, that is either a 0 or a 1, right? Rather than writing 0, 1, 0, 1 arbitrarily, they use this kind of shape. And so what it's showing is that on the cycle number 1, if they have the rising edge, let's take this on the MISO, right? That's all it's saying. That's as far as you really need to care about. But you can also change to C polarity is the falling edge, and then you might want to do the CPHA is 1 so that you're still in the middle of the clock, right? Make sure that whatever edge you're triggering on falls in the middle of your bit, right? Because otherwise you end up with a race condition, which is not politically charged. All it means is that if my clock has a rising edge here and my data has a transition here, which one comes first? The answer is we don't know exactly. Yeah, they wiggle back and forth just a little bit because nothing is perfect. And so your data is going to sometimes look correct and sometimes look wrong, and you don't necessarily know. In fact, we had someone in here with one of their labs in the UART where like 30 out of 31 times it was the right value. And then it would tick over and be the wrong one occasionally, because the race was won in the case of the clock most of the time. But every once in a while, it would go the other way. Because the clock placement is not like this predictive deterministic location. It's got this probability distribution over a range of which it might jitter. Okay. This is really all you need to know, is we have to read this kind of diagram and go, okay, 0, 0 means rising edge of clock falls in the middle of 1. We've got our data. You're going to have to build your state machine in order to build this transmitter based on the data sheet for the component that I'm going to give you. Fortunately for all of you, the data sheet that I'm going to give you comes from Vigilant, I believe, and they are designed for kind of hobbyists. So their data sheets are very easy and simple. So we'll start out nice and easy, which should hopefully be well within everyone's capabilities. You are going to, if you remember your boards, can I still this real quick, thank you. It is going to plug into one of these little connectors on the end. So it's a little adaptive module, little handout that just plugs in right there and adapts and expands the capabilities of this board. Make sure that you understand the constraints file so that you can map these pins with the going on inside the FPGA, right? That constraints file tells physically where this is versus logically inside the FPGA. That's how they communicate, is that constraints file. Very clearly labeled on the bottom 2 pins of this, if I'm oriented this way, is ground and then 3.3 volts. If you're using a multimeter to measure voltages, be very, very careful to not short those 2 together because you can break your board. You won't necessarily break your board, but it is likely. It has over voltage protection. It tries to save it, but it won't necessarily be successful. Yes, that's all. So we're going to relocate to the lab. I'm going to go to my office and bring a whole bunch of little D to A modules to hand out to you guys. And you will start finishing lab 2 or reading up on lab 3. So that we can all be at least started on lab 3 by lab on Wednesday. I guess I should say, you guys don't have to listen to this, just for people on the video. If you didn't make it to class, I have an exam scheduled on the calendar for next Wednesday, but I'm going to bump it to the following Monday so that you guys have the ability to study over the weekend rather than having to cram in on just Monday night and Tuesday night after I do the review, which is hard for a lot of working people. Oh, yeah.
Color, text,